It's almost a full house. Traffic today. Okay. Graphing these three graphs on three different grids. Wait, who's missing? Quinn? Who's missing?
No.
Okay. That's right. Make sure your neighbor's okay with all these. At some point. Here's some test corrections. Are we done? Just a minute. I'll be calling some. Well, maybe I'll be fine. Maybe not. Okay. The first one, y equals e to the x. Would you please take your finger and show me what this looks like from your perspective? Should look like this. And the point that you can show me, the coordinates of the points you can show me are 0, 1, correct? How many points do I care about? 3 if you're making a good graph with this. So 0, 1, also 1 comma 1 comma 1 comma e, which is approximately 2.7. So like right there. So and then of course negative 1 over e, which is approximately about 1/3. Now, that gives a nice line. I could just make a nice line going right through that goes down forever. Is that right? No, of course not. It has a floor, which is called the horizontal asymptote. Yeah, is this what y'all have? If for y equals negative x, show me what we're going to do to this graph. Right over that y-axis, right? When the x's are being negated like that, it's just looking. Okay, for this one, I'm going to put this one right here. Can you show me what the 12 is going to do to our first function? It is a vertical stretch. So specifically, like most notably, that 0, 1 is going to become 0, 12. Are we good with that? And that 0.25 with the x, can you show me what effect that's going to have? It is going to be a horizontal stretch. Why is it a stretch? It's a stretch because less than 1 and greater than 0, right? Between 0 and 1 is going to be a stretch. Specifically, a stretch by a factor of, are we good with that? How do we know it's 4?
0.25 is 1/4.
Yeah, 0.25 is 1/4. We know that it's the reciprocal. So what point will that affect? Let's talk about 1 comma e. That's going to become 4 comma 12e, right? So it's got the horizontal stretch and the vertical stretch. So where should I put my 12? Do I need more room on this graph? So scale it differently, right? So I just put that 12 right here, and we know it's going up like this. And like here's my 4 now. If I want to point on there, then this point is for sure. What did I say? 12e, is that right?
Yeah.
Which is approximately 30 something, 34 maybe. Does that make sense? 30s. As you know, times 3 would be 36, so 2.7. Maybe less than that. Maybe 32. Yes.
The asymptote is an X.
Oh, thank you. Let's continue this. Where's the asymptote? Still 0. So yeah, this is gonna kind of decrease slowly to that. Thank you. Yeah, it doesn't start at that y-axis. So, and it kind of looked the way I drew it. It kind of looked like it was about to level off there, but it can't. Horizontal asymptote remains. Any questions? Yes, Kieran.
Way that you make the horizontal asymptote like something other than 0 by like a vertical shift upwards.
What do you guys think? Is that the only way to move a horizontal asymptote? Well, will a horizontal stretch do it? No, and a vertical stretch won't do it? Because 0 times anything is 0. Yeah, you're right. The only way to get off that floor is lift it, add something to it, or subtract, take it down. I won't be talking about that today. I like your foreshadowing. Next level. The last day of the unit, guys. Shall we cherish this day? As we do every day? Let's do it. Okay, more applications to exponential functions. Back to the packets. You're going to see this phrase from time to time. The law of uninhibited growth or decay. This applies to population and money. So we've already studied this actually. So when I think law of uninhibited growth, in my mind comes this: A equals P times E to the RT. And you can always use this when it's talking about law of uninhibited growth. I don't want you to think that we're dealing with a completely different formula today. But you may see it look in this form. A of T equals A naught of E to the KT. They're the exact same thing, just using some different letters. This K is called the growth rate, just like it is with money. If that, if that K is positive, we're talking about growth. If it's negative, it would be a decay rate. Do you remember how the vocabulary used for this sub-zero?
No.
What is it?
No.
Not, right? The A naught. This is the starting amount. Which makes perfect sense with the P, doesn't it? Because P is the principal, which is the starting amount of money that we're dealing with. It's the exact same thing we've been doing. So we're kind of just delving further into this and seeing how it can be applied in different places. Like here, the size P of a certain insect population at time T in days obeys the law of uninhibited growth. So let's take a look at this. Now it told us it obeys the law of uninhibited growth, so it didn't need to give us the equation. But can you imagine what this graph looks like? Can you discuss with your neighbor what this graph looks like?
Yeah. Horizontally, 0.0. Very.
Okay, so we know that the y-intercept is, the y-intercept is 0, comma 500, and that 0.02 does what? Yeah, it's a horizontal stretch by a factor of 50, but it is still growing, isn't it? Still growing. So let's kind of keep this in mind. Determine the number of insects at t equals 0 days. Now you could plug in the 0, you could think about the graph and say, oh, I know the answer already. Does that make sense? We know that it is 500. You could plug in the 0 if you like, if you feel more secure with that, then that's fine. 0.02 times 0, e to 0, of course, is 1, both without work, but you could just say 500. That's the way it works. What is the growth rate of the insect population? Yeah, normally we talk about percent. You could say the rate is 0.02. Normally it's given in percent, so 2%. The population after 10 days, I'll give you a moment to finish C, D, and E.
What's the balance of your number?
What's the population? So should we round up or always round down? I don't know if it's 0.98. I don't want to take away that light. 0.6?
Yeah.
Well, yeah. But this is an insect population. You have half an insect. I will be calling on some people to help us out with this. Hopefully these problems are very comfortable for you. Thankfully, neighbor, I'm about to call on some folks. Make sure they got it right. You ready? Ready or not? See what you got. Brandon, what'd you get for C?
610 instead.
Do we agree? Thank you for the unit. And you got that by doing what?
Putting in 10 to T and calculating.
Okay. Are we good? Brandon, I feel like maybe that was too simple. Do you want to do D also? You want to give us an answer for that one?
So I set 800 with 500 e to the 0.06, and then divide by 500, so you get 8 for 5. Equal to e 0.02, and then I put it in log, so 0.02 c 0 ln a over 5. and then divide by 0.00.
You got
23
the 3.5-ish. What's
days.
days? Are we good? Round to do.
No, yeah, but it's 23. That's
It's 23.49.
cheap rounded to 24 days. Like, wouldn't that make sense?
It's kind of judgment call, isn't it, with these? And like, what is it from asking? Could we have half a day? Yeah, like, do insects reproduce like 24 hours a day? No, do they sleep? Do they wait till I wake up to? I don't know.
Possible.
I need to talk to a science teacher about this. But 23.5, if you want to give me a 24 or 23, that's fine too. As long as you're showing me the work, give me a thoughtful answer, I'd be quite happy. Brandon, thank you. Andrew, Australian.
For E.
Yes, for E, please.
So I set A equal to 1000.
Okay.
So 1000 is equal to 500 E to the 0.02 times T.
Can you cut to the chase?
Okay, so the answer.
Yeah. No, I'm not to be rude, but I think I kind of went through that process.
34.66.
34.66. No, that's exactly. I'm sorry. I just wanted the startup to make sure that you set it equal to 1000, and then after we did the other ones, the process is exactly the same. Do you have any questions? Yeah, thanks, Andrew. Would you, just out of curiosity, would you be comfortable jumping right to this for like doubling? Would you be comfortable doing something like that?
Would say so.
Because you could make some little shortcuts for yourself. It doesn't. You don't have to do every little step. Just what's important to you. Okay, let's continue. Strontium 90 is a radioactive material that decays according to that function. Wait, how do we know that's a decaying function? It's a negative up there. Where A naught is the initial amount present, we knew that, and A is the amount present at time t in years. Assume that the scientist has a sample of 500 grams of strontium. Yeah, I think we used that 500 before. Let's make it something crazy like 600. Yeah, because you gotta live a little. It's Valentine's Day. Come on. Would you please discuss with your neighbor what it means if a element is radioactive and what half-life actually means? Like your knowledge from your science class and just living.
Yeah.
Yeah.
This is the carbon 14 on there.
Okay. So radioactive material, what do you remember? So carbon 14. I heard that come. Do you guys remember carbon 14?
No.
Sound familiar? Carbon 14? What does it mean for an object to be radioactive? Do you know? I heard something.
Does it emit radioactive? Yeah.
Yeah, it emits radioactive energy. It emits energy. And does that energy stay constant over time? No, it slowly kind of burns out. And depending on the element that is radioactive, it'll burn out quicker or faster. Are we radioactive? Yeah, all living things are radioactive because we have carbon 14 in us, which is a radioactive substance. It's not like plutonium kind of radioactive. It's not that dangerous to be near us unless there are other issues. But so if it's decaying, what does that mean is happening to the element?
Getting this.
Getting more stable. So is it like getting lighter or something? Is that what's happening?
Less energy.
That's radioactive energy. So what's happening to the radioactive elements? What's that?
Decreasing.
They're decreasing. So does that mean it's gonna like just shrink away to nothing? Like just kind of be gone one day? Like what happens? It's not gonna go away.
It's gonna lose. Stable count.
It changes into a more stable counterpart. You're right, that radioactive elements lose isotopes. Does that sound like something you've talked about? Like changes, like they lose some isotopes and they change from like strontium 90 to maybe strontium 50 or something like that, right? They change their nature. So it's not like it has a different mass, but the quantity of energy emitting elements are gone. You don't need to know any of that for this problem, though. You just have to know that function. It tells us. We know that the decay rate of this strontium 90 is 8.7%. Would it be appropriate to say negative 8.7%? It's asking for the decay rate. So if you say
Already
Thanks.
implies that it's
it implies negative. If you say it's decaying at a rate of negative 8.7, it's growing. Scary. How much strontium 90 is left after 10 days? I feel like we've done these problems. Maybe go down to the just D. Yeah, just D.
Oh, is there no photography?
There was one, but it's completely ineffective. So
Oh, okay.
check with your neighbor. I'm gonna call on someone in about 10 seconds. Okay, D. Chazzy, can you help me out with this one, please?
Sure, so I just want the, are you doing like the negative 0.0 e half?
87T equals 1/2. Are we good with this?
Zeros.
Oh, zero. It's not 87% decay.
Yeah,
0.087 T equals 1/2. Are we good with that? Starting there even? Okay. And then what did you get from there?
and then I just did e equals not log 1/2 over negative 0.07.
Natural log of 1/2 over negative 0.087.
And then that would be 7.97 years.
7.97 years. Are we okay with this?
Yeah.
Is it okay to round to like a hundredth like that? For years?
Yeah.
Definitely. Radioactivity is decaying 24/7. Right? It does not sleep. Doesn't have a weekend. Yeah. Moving on. A culture of bacteria obeys the law of uninhibited growth. If n is a number of bacteria in the culture and t is the time spent in hours express n as a function of t, it doesn't give us an equation here. How are we supposed to do this? I'll give you a chance to do it and check with your neighbor. Make sure they got the same equation you did for A. Just A. We'll do B and C together. At least B. Actually, I'll go ahead and do A. N of t equals n naught times e to the either RT or KT. I couldn't care less. Yes, Jazzy?
What is the, why is it in the end not, there's just a different than the end on the left?
N on the left is changing. N is a function of P. N represents the number of bacteria in the culture. That means it's growing. But this number can't grow. It's just, it starts with a number that can't be changed. Yeah, good question. So that K represents the growth rate. In order to figure out how many bacteria are on this culture at any time, we have to see exactly how fast it's changing. How do we figure out that K? With some data. That's what they have to tell us in B. So if 500, right, there's 500 again. Should we change it? No, okay. See the 500, 800. Yeah, I'm changing that to 620 because I can. You can't do that on a test, okay? You can't just not like a number. If 620 bacteria are present initially and there are 800 after an hour, how many will be present in the culture after 5 hours? I'll give you a moment to work through this. You ready? Should talk it out.
Yeah. I think. Okay, so 5% difference in total.
Oh, I see. Okay. See, Henry, can you help us out with this? Were you able to get anywhere for B?
Oh, yeah. Um, oh, yeah, so you do, 800 divided by,
Yeah, before we're dividing anything, I think we need to change the formula a little bit, don't we?
oh, yeah, you use, a logarithm that it becomes, a natural log, so ln
So even before that, we know that and not is.
of 620.
We know that that's 620. So our more specific equation is 620. So I imagine you did that and just went about your way and you said that n of t here equals
800.
800. Okay, and then I'm sorry to interrupt. So from there,
You divide 800 by 620,
okay,
and then you take, the logarithm of that, so it's ln, 800 over 620 equals, k times, t, and since t is 1,
yeah, I forgot to put this one in there.
so, you do the ln, the natural log in your calculator, and then it was about, 0.2549.
Okay,
Then you take that and you put it into the formula as, the k, so it's, n of t equals 620 e to the power of 0.2549 t, and then we do that to the 5 in we do times 5.
Okay,
And then you just put that in the calculator, and it was 2,217.69.
217.69. Should we count the 0.69 bacteria?
Oh no,
So we just cut it down to 2,217.
yeah.
Are we good with this? Chazzy?
So when we're like rounding these problems, we shouldn't round them to
Thank you. Yes, so that's exactly what I want to mention. This number here, I've rounded because I don't know the rest of the numbers, but hopefully when you're doing this, you grab the number and actually put it in your equation. You all know how to grab that number so that you don't lose a single digit. Don't retype, you just go up and hit enter. So that'll grab it wherever you want to put it. So Henry, have you done that? Was there a little bit of rounding?
Oh yeah, I did. I rounded very bit. So
Okay, I'm not just gonna do the same thing, but maybe it's gonna be a little bit more. If you grab the whole thing, does it make it up to 18?
Yeah.
It does?
No, when you round.
When you round it. Okay, so is this an appropriate answer? Okay, I'll take it.
Would be round to like 15 digits.
Around to 15 digits. I think you'll be fine if you do that. Unless I want 18 digits of accuracy. Highly unlikely. How long is it until there are 20,000? You know how to do this, don't you? Did I skip? Did I go on? Okay. Newton's law of cooling. Okay, let's talk about the idea of this first. And don't jot this down just yet. I'll tell you when to jot it down. Is there a pizza place called like Blaze 800 or something like that? Is that what it's called?
Used to places.
Are they?
Blaze, that was like,
Oh, 800 degrees. Okay, thank you. 800 degrees is what I'm talking about. It's called 800 degrees because yeah, that's when they cook the pizza, 800 degrees. Okay, so let's talk about the story of a pizza as it's released from the oven. Okay, so obviously, I guess it's going to start at about 800 degrees. And again, don't write this down. So once you take it out of the oven, time will be ticking. Does it stay at 800 degrees like this?
No, not quite.
No, it doesn't. So it's going to do something like, I don't know, maybe this. Do you think that? That's not supposed to be warbly, it's supposed to be a line. Does it do that? No, go ahead and discuss with your neighbor. What's the temperature going to do?
Yeah, I
Okay, so show me what it's going to do from that 800. We're going to do this. No, it does decrease it quite quickly, thankfully, right? Otherwise, it would be very difficult to eat. And then what's going to happen?
Balance.
Flat line.
It flat lines to room temperature. So let's say room temperature is like, I don't know, it's pretty hot in this kitchen. So if this is 80 degrees, then it would do something like this, wouldn't it? Where this is room temperature. Does that make sense? Over time, it'll cool to be about room temperature. Maybe a little bit less than room temperature. Would that be possible? Would it be less than room temperature? That seems unlikely. Is it ever actually going to be room temperature?
It could be.
Depends on when you eat it. I think honestly, if you let it stick long enough, it probably will be room temperature, but mathematically speaking, which this is just a model, it will never actually be there. So this is called Newton's law of cooling. And now if you want to start writing, you may. I'm going to replace these though with different things, like this is our T sub 0, T standing for Oh, I'm not, sorry, not U sub zero, different U sub zero. U standing for temperature. This is T, which is the temperature of the room. Newton's law of cooling says that we have a function that looks like this. What letter do you think is going to be involved? Besides U and T. E, yeah, it's exponential, right? This is just another application. So this, according to Newton's law of cooling, U of T is equal to T plus minus T times E to the KT. So we know what E to the KT looks like. We know what E to the KT looks like. That's either increasing or decreasing. This here represents a vertical stretch. It would make sense that this is it. U naught minus T, the temperature difference there. And then this T here just takes that whole function and moves it up, right? So like Karen was talking about, we could move that horizontal asymptote up. That is Newton's law of cooling. You have to memorize it. You have to memorize the other one we're doing. A equals P times E to the RT. This one will probably, well, this one will be given to you if you, and you just have to know how to work with it. So let's see if we could do that. Thermometer reading 72 degrees is placed in a refrigerator where the temperature is a constant 38 degrees Fahrenheit. The temperature reads 60 degrees after 2 minutes. What will it read after 7 minutes? I'll give you a minute to go through this. Be right back.
That's 30. That room's a constant. 72.
Yeah, you have to plug in the 60 first to find the rate. Speed is an hour. Wait, what is the T? What in terms for time?
Yeah, so security.
Yeah, there's a little T, there's a big T.
Like, the one in exponential.
Is it like
hours?
days?
Time. Oh, it depends on what you're talking about. Like here, it's talking about minutes. So
There would just be seven.
yeah, just keep it consistent. You don't have to do it in days, but yeah, minutes. And time is a minute. Good question. Okay, so we just kind of follow our nose. And the temperature read 72 degrees. That is the starting amount. That is 72 degrees is U naught. So UT is equal to, do we know what T is equal to? It's 38. That is the room temperature. Plus 2 minus 38 times E to the, first I could do KT. This is kind of a general. We have to figure out that K, which is the rate of TK or rate of cooling in this case. So it tells us something that after 2 minutes, so 2 minutes, this is 38. Plus, what is 72 minus 38? 34, is that right? 34 e to the k times 2. All this is equal to 60. Did you do this? Solve from there. Who got K? Really? 8. Did anyone else get that? Thank you. Does it make sense that it's negative?
Yeah,
What do I do with that?
so that is a K.
Yeah, this is our value, and you plug that in. I also plug in a 7. I think you get the answer. So you have 7. 38 plus 34 e to the negative 0.218-ish times 7 gives us 70, 72. Is that right?
Oh, wait, no. For
The answer is subtract 38.
The 7.
What is it?
The 7, or you parentheses 7, 7.
Oh, you have 7 equal to that, yes. Brianna, did you get it?
Oh, yeah, I got 45.39.
45.39. Let's just say 45.4 degrees. And the other one was unitless. Any questions? Yeah, I'll give you, let's see, how long will, can you imagine how to do this? How long will it take before the thermometer reads 39 degrees? Is that equal to 39? And for the other one,
Is that equal to 45?
is that equal to 45? Yeah, I think. What do you think they want you to notice as time passes?
Temperature.
Decreases to room temperature. But that's just the whole idea. I think once you have the concept, it all just falls into place, I hope. It started at 72 degrees and it is coming down. We're able to figure out that rate, so you can get all that other information about it. Logistic models, last application of the last section. Let's go back to that Petri dish, shall we? If it's truly uninhibited growth, now don't write this down. But remember, it started at 500. Again, don't write this down. Start at 500 and then goes up. How far? Infinitely. So bacteria are pretty small, but if this is going up infinitely, eventually it's going to overrun that Petri dish, isn't it? And then it's going to eventually overrun that laboratory, isn't it? I feel bad for the people there. And then after that, if it's going up infinitely,
Takes over the world.
it's going to take over the world. Eventually, the universe. It will fill the universe with bacteria. It will be swimming in bacteria. Unlikely. Right, so there's very little that's uninhibited growth. There's something that inhibits growth eventually. There's a ceiling, isn't there? It is the carrying capacity. How many of you have studied carrying capacity? And another, nice. What, so does it look, is it logistic model that you've discussed before? So in biology, do they call it a logistic model or do they use population?
It sounds like it has a plateau. Carrying capacity is a top.
Yeah, so logistic model, and if you want to copy this down, you can do that. So it says that a population has, by definition, population has to have some sort of starting number in order to grow. 0, it just can't grow. It says, yeah, it's going to be exponential for a while, but eventually the environment is going to play an effect and start limiting the growth until it just can't grow anymore until that population reaches, what did you call it? The carrying capacity. So that's going to look like what?
As
It's gonna be an S curve, and the carrying capacity is going to be a horizontal asymptote of this S curve. And this is normally called C. The point where it changes from kind of exponentially growing to just like, whoa, there's something going on. That amount would be half of C. And if we were to continue this model, now this would be purely like theoretical, it would actually continue. But normally a timer starts at 0 and then increases. Yes,
And
Andrew.
what happens to half C again?
Oh, what I'm saying is, as time increases, once the population gets to half the carrying capacity, something changes, like it can't reproduce as quickly as it did before. There's something inhibiting the growth. So although the population keeps going up, it's more difficult to find food or for all the offspring to survive for some reason, or there's illness that may take place. So there's something that makes the carrying capacity what it is for a particular environment. So this logistic model is an exponential type of function. So let me see. I haven't memorized this. I almost have it. I think I have it. P of T. Let's see, maybe I do have it down. Equals C over 1 plus E times, I don't want to write this. One moment. E to the negative BT. A times E to the negative BT. It's a little a there. Get this out. They're all lowercase. In this case, negative B.
We don't have to memorize this formula.
You don't have to memorize it. But what you do have to know is that C on top represents the carrying capacity. And that B is the growth rate. And it's not a consistent growth rate like most exponential models. This is a logarithmic or the logistic model. And this will be derived when you get to calculus. You're going to see where this comes from. But for right now, it's out of the scope of this class. It's not necessary. So please trust me that populations follow this model. There's plenty of resources, but there's a limited number of organisms that an environment could support. Chazzy, thank you.
Did the graph start like sort of halfway from half C, I guess, because like you have to have a starting amount of bacteria. Like, what's like the reason why it starts not at 0?
You're talking about this one?
Yeah, why is it start?
Well, if a population is 0, has a very hard time growing. So it can't be 0. Now we could jump in any time in this logistic model. Right, so our time 0 could be here. Our time could be earlier in the stage of growth of this population. I just happen to do it here. So this is not like half of the half or anything. This is just an arbitrary point here. This is the initial population. And notice that initial population is not in our functions.
No, if you think about it.
Karen, and then Andrew, Karen, do you have a different question?
What about our population? Are we at half C yet?
Oh, I don't know.
Okay.
I think we keep changing the carrying capacity with like agriculture, innovations, finding new space, but factory farming. Yes.
Those populations actually, they stable carrying capacity.
Oh, yeah, if the carrying capacity exceeds it, you're right, then it's like the environment says, whoa, comes back down. Okay, it's just a model.
So you don't have to like worry about that.
But yeah, that would be some sort of weird sinusoidal stuff going on. It's interesting. Good point. Okay, you got A, B, C, D, and E. Let's see what you can do with it. So this is the percentage of Americans who have social media profiles, where T represents the number of years after 2008. In 2008, how many of you had social media profiles?
I wasn't alive.
Not alive. Okay, so that's a no. Answer the question.
I might have had a social.
Okay. You never know. Someone anticipated. Okay. Any of you live in 08? Proportion of 08 at least? 07, anybody? Oh, 06, really? Nice. That's a good year. Guys, when's your birthday?
July 7th.
You're July 7th.
Second.
Right.
I'm July 7th. Well, I wouldn't be asking.
Wait, no, 6 or 7.
7.
Wait, what? You're old. Young
It's
for
no, I'm not gonna see the regular.
No,
you're young, you're young.
you're old.
Yeah, as long as this.
Back.
Flip it over to the house.
So make sure that when you graph this, for C, make sure you see that nice S curve.
It's one, so 2.12 times one.
Why in this form, you can't have half. It's still one.
Oh. Oh, you're right. You have a growth rate.
It's not that too.
So how does this fall? Wait, how's that? No.
No.
Oh, I know. Wow.
Oh, no, because it's part of the equation.
It's doing 86.1 plus 36.2 E to the.
Yeah, so it's doing
86.1.
Yeah.
Right.
So what did you do there?
It's this.
I did.
Oh, because the equation is E to the negatives.
Oh, by the way, E. Oh, it's the negative, that's the bottom of the E, I guess.
Looks like either. That's see, so many things. I'm gonna search 8 years to be.
We're able to see the full curve on your calculator.
No.
Make sure you're adjusting the window appropriately.
Yeah, that's true.
I recommend hit Windows. Play with the settings.
Oh,
It's a model.
there it is. Oh.
I mean, this one.
Anyways, 11 is 17, 79%. You definitely move on.
Yes, you did. I like that.
You made a big mistake. Let's see if you can stop the mistake. Oh, no, parentheses. There you go.
About ready to go over these? Andrew Higashi, can you help us with A? I'm sorry, a little bit louder. 27.6. Is that right? Okay, and what does this represent? The percentage of the population that had social media in. We're good with that? Yeah, so percent, et cetera, social media, people who had social media in 2008. Thank you. Growth rate is not negative 36.1%. 36.1%. And notice in the notes, B is a growth rate. So if it's negative, going up. If it's positive B, as if you see it like a positive point something, it's actually going to be decreasing to 0. It's going to be coming from the carrying capacity. What's that?
In a fraction.
It is in the bottom of the fraction. I think the role has been reversed. Right, if that 1 weren't there, you could imagine that negative would just bring it to the top. I hope that you saw this, and I hope that also looks something like this. With numbers of 2017, what percentage had social media profile? Miles, did you get something for this one?
I didn't do the math yet, but like I know.
So you would just plug in a
Plug in, the T, solve the.
exactly. So yeah, so this is really just finding P of 9, isn't it? Plug and chug. Did anyone get that number? Did you crunch the value? Yeah, Andrew?
That's 79.55%.
9.55%. Did anyone else get that?
Yes, sir.
Good, thank you. In what year did 69.3% of Americans have social media profile? And what year was that? Yes, Brandon?
2014.
2014. Are we okay with that? And my final question to you is approximately, and please discuss this with your neighbor. If this model holds true, in the year 10,000, what percentage of the population will have approximately social media profiles? Please discuss with your neighbor. In the year 10,000, approximately what percent of the population has social media profiles?
Oh, yeah, we'll be like.
So what am I asking here?
Yeah.
The answer is 86 point
Oh, no.
no, 99999. Right, we're really close to 86 or 86.1, maybe 86.1. Why not 100?
Is the carrying capacity.
Why not just everyone have a profile? It's kids, and it's kids, babies. Yeah, very few babies except Kieran. Had social media profiles. Why don't you make a profile for your kids
Right now.
right now? Let's say you've had one since 2024.
You make a profile for your kid.
Okay, folks, that's all I got for you. Hope it made sense. Hope you enjoyed it. I do have the time now to give you to work on your assignment.